25 minutes.
I need to check if we're fine.
And just open the doors.
Okay.
Is it shaking?
Yep.
I will. Just turn it off. So after your Yanagihara, before I forget, let me give you your. Okay. Rather finish printing there. Oh, and your tea is up here. Okay, thanks. All right.
PBRC. Brian used to work for PBRC. Friend.
Okay, now Jason's done. That's a good idea.
Hold on to this.
How are you?
I had a question. The other kinds of box jellyfish that are around here. Here in front of you, there are several that we don't know about.
Right.
Are there any brochures that show descriptions or papers?
Papers.
I
Do you have my email?
don't even have my email.
Okay. I'll give you my card if you'll write to me. I can send you some papers.
It's just that strange one from last week.
Yeah.
When I was on the beach, well, my mom was down there. She brought back a story that was completely different than what the life was we're seeing afterward. So it's time for me to be free at home. I see it.
You too.
go ahead here.
Yeah.
You know, Australia being a bad place, are there any places other than that that are starting to get worse?
Well,
Jellyfish.
actually, they have been worse for quite some time.
We got all this
Under all the black. So, so actually, the most loss of life here more than Australia.
Islands offshore.
On the coast.
That's kind of industrial.
Well, that's our everywhere.
No one survives to tell the story. No,
I
that's
had
all.
it there.
Dr.
Oh, nice.
How are you? Good to meet you. Yeah, we're with the St. Augustine's Church, and we've been doing this now for 9 or 10 months. And we'd like to, whatever we can do to help you with the research, we can help you do.
So, folks usually go out about what time?
Usually it's sunrise,
It's sunrise.
which is really nice.
Do you have anyone who might like to get up at 4 a.m.?
Well, no, if it's best for you, we can do that. I mean, we just figured, we went down there with the concept of trying to clean the beaches before the visitors come down. And then also educate the visitors around there about the residents.
So the way is collecting the animals to harvest the about chemistry. So basically, we're going to be there regularly. Set up 4 hours.
Sure.
And do you have folks who are also walking?
Not usually, just usually on the beach.
Well, fantastic. So there's actual pictures with the animals.
I know, but we're sure. Yeah, I don't see it.
So it's a little more of a delicate process.
In here, or
Sometimes it's yes, I do, yeah, depending on how long we've been out there on the sand.
But, no, yes. And we actually also would have a presence to have one scout. So, folks are in
It would go from, I started this out on my own, and actually I was disappointed when people came with me because it's such a nice walk in the morning. But, sometimes things tend, so usually there's 3 or 4 of us.
well, so because it's a heavily so there's
See, there we live there.
but basically
We,
I sometimes have a hard time.
Well, it's nice when, you have some flexibility, and I know that as undergraduates graduate, and sometimes you have trouble with continuity. Some people are going to be enthused, and others not as.
Yeah, I'm not, I don't know, what's your name? Richard Small.
Robin Bond. Remember Robin?
Yes.
After the presentation, you get 2 minutes of your time. I thought did you give him a card?
No, I didn't.
Oh.
Is he carded?
You're not giving me a card?
What do we need to go?
You don't. We need to get over.
So my great grandmother is tall.
Oh, good.
My father's grandmother is tall.
Where?
They start out.
Okay, no, I'm more Pennsylvania, Erie, Northwest. We've gone back to 16.
Super cheap.
Yeah, well, I've got 2 of those books that or you can go back.
On the right side of the bed.
So you get like people that are really
Right, so I have schedules based upon the night tide, morning low tide, moon tide.
I'll be.
But, once we get 2 books in,
It's in California. Well, Huntington Beach. We went there.
or what I do is I put the
Couldn't afford
phone
it.
out for my folks and say, implementation of the law.
Yeah.
And for the most part, they seem to be able to.
Well, but yeah, we go all, all the time. It's all in Route 1. We're there every day.
So, usually get into
But summer, usually it's around 6 days.
I can't hear what I'm.
Especially winter time, it's so dark now.
I hear it.
Yeah, but that's kind of sad.
So
You're
we
gonna
like
do
to
it
go
better?
out there, depending on the concept, to 4:30.
Anyway, these.
They don't have to do.
So what sounds like you're gonna do, what I'd like to do is, I like to do this myself before I get something. So that I can go through the process to make sure that everything's working.
And we went to visit them. We spent quite a bit.
I'm not sure. I don't know if we're gonna be able to do it for Monday, but I'd love to do it.
She spent.
It's a pretty funny day.
Sunday.
Sunday I'm available.
Well, let's, what's drama?
Okay, yeah, well, everybody gets bounced back. And everyone says that to me, that's the way my wife said it. Everyone gets rejected first until we accept.
Well, we didn't write it.
It's horrible. Well, that could be a problem.
Or blink and I'm like.
Yes, if you give me the information, I'd love to see the lab. So,
So we
perfect.
have it air conditioning.
So give me all the information, we'll set up a time on each
But
other.
when I turn it on,
Okay.
it shakes the projector. So you could be cooler with the shaky screen, or we could.
On now.
It is not on. I cannot, because it's a nature preserve, I can't. It's, you guys feeling okay? The door will stay open like that. And once the sun is completely down, it will. You guys all right? Just wanted to make sure.
We have about 5 minutes before we start. And then would you like to take your questions at the end? Yep, understand. Okay. Okay. All right. And
Did your link drop at 1 hour?
no, it's unlimited. Yeah.
I've done that
Yeah.
before.
Yeah.
And then people in town were like, oh, this happened.
Yeah. We're up and running, so we're good to go. Remember to use the microphone so that people can hear you. And the setup, I mean, the breakdown of converting this room back into general public use is fast because we only have about 15 minutes to do it. So what I'm going to do is, if people have questions for you at the end of their talk, I'm going to just say go to the water cooler over there and you can address their questions there, because we're going to have to move all these chairs back and put back all those stanchions there. It's kind of like a busy thing. And I still want you to answer all your questions and stuff individually to people who want to come up, who want to meet you. So I'll just refer them to the water cooler. Yeah, yeah. I will be. There is a meeting that's going on up there, the board meeting. A few of the attendees will come back to the show. And people will just put themselves in. It's 3 minutes. We're good. Yeah, we're live. Everything is set up. We're good to go.
You want this door left open?
Does it help the cost base? It helps the cost base.
I'm not yet.
Usually it does. But I won't leave it open as much.
Yes.
When I go out,
Oh, perfect.
over there.
Anything else we need to do?
No, I think we're good to go.
Cool.
We're definitely good to go.
I'm gonna go direct some more.
Okay, sure.
Oh, no, I was partially.
Here. I see the resemblance. Yeah. We have two, right? Right? Boy.
I can see your invention in action a couple of weeks ago. We were out diving and some of the people had this thing all over. Jules, you know? Jules had the kids in the carrot.
A couple more seconds. Well, aloha, ahi ahi, and welcome to this evening's Theater Thursdays here at Hanauma Bay. My name is Mahea Lani. I'm the Outreach Specialist with the Hanauma Bay Education Program. We are continuing to learn about interesting invertebrate investigations, and it is my pleasure to introduce Dr. Angel Yanagihara, whose talk title is Taking the Sting Out of Box Jellyfish. And with that said, let's just give Dr. Yanagihara a round of applause, and let's get started.
Thank you, Mayalani, for that nice introduction. It's a real pleasure to be here today, and I appreciate the invitation. I've spoken to this group over the last 17 years a number of times, and it's always nice to be with kindred spirits who are dedicated to reef preservation and to healthy ocean use. Tonight, I want to start out by just asking for a show of hands. How many people have been stung by a box jellyfish in this room? Okay. Has anyone had to go? I can't count. Has that led anyone to a trip to the hospital? No. Okay. So that's the good news then. For the most part, stings in Hawaii by box jellyfish don't result in trips to the emergency room. And as far as we know, no deaths, or perhaps arguably 2 or 3 over the last 40 years. I might put my vote more towards the no deaths, but it's definitely a problem here for us, significantly in Hanauma Bay for some interesting reason that we have yet to discern. But tonight I want to give you an overview of my research path, which started myself off of Kaimana Beach in 1997, and I signed out against medical advice after being attended to by an ambulance crew, and they weren't happy that I refused to get in the ambulance, but I was treated there at the Waikiki Aquarium in their hot water shower. When I got home from that horrible event, I really then regretted my pride not allowing me to go to the hospital, and spent 3 days in agony. My husband's a physician, and between the two of us, we would try to do all the typical things one might do for a topical dermal pain and urticaria, as they call it, wheals and welts, but nothing worked. So as a biochemist, this situation got my goat, and I decided I want to find out what is this thing. So I did a literature search, and I found actually only a few papers from the 1920s and a couple from the 50s, and one locally in Hawaii that was about 20 years old. But for the most part, there was no biochemical answer to my question, what was in the venom. So I looked to see if there might be any funding mechanism in Hawaii, because as a biochemist, that's what I do, is write grant proposals. And I found Hawaii Community Foundation had a call for proposals. So I wrote a proposal, but I broke all the proper rules of grantsmanship. I didn't compliment the previous work. I pretty much eviscerated everything that had been published, and complained that it had never been done rigorously and properly, et cetera, because it was just an exercise of my own black humor. I didn't think that I would be funded in a million years, being an old school biochemist, not a marine biologist, et cetera. When I got the letter 3 months later from Hawaii Community Foundation, the joke was on me, because I was funded. And now I had to do what I complained no one else had done properly in 80 years of research. So this talk tonight is going to be kind of a whirlwind tour of the last 19 years of my research path. And you'll see that I've worn a lot of different hats, and I've learned a lot of different things along the way. I've become scuba certified as a scientific diver through the UH program. I've now dove with Special Operation Command divers. I've become something of a field ecologist. I've done a lot of electron microscopy and cell biology. I've circled back to my own wheelhouse skill set of biochemistry, but then I've taken this in what they call translational pathway to bring something of use from the lab back to the public, back to the beach. Yes?
Short childhood background.
a short childhood background. I was born in Anchorage, Alaska. My father was in the Strategic Air Command, Special Operations 7th Air Force. We moved around a lot growing up. He taught me to dive at a young age. I've always been a water baby, but I went to 12 schools in 12 years and met my husband, who's a local Hawaii person, at Georgetown in Washington, D.C., my PhD program. Okay, so I want to now kind of take you quickly through the path of the process. So when I was stung, the first thing I asked,
Can't really do that well. It's either like all off or
Over there.
Here, I got you.
the first thing I asked was, what are box jellies? People told me, in fact, that morning I was warned, don't swim because there are box jellies. I saw them on the beach and I thought that couldn't possibly be a problem. And I'm sure many of you have that frustrating experience with folks who aren't used to Hawaii, telling them not to go. So with regard to where they are in the animal kingdom, interestingly, they're almost at the very base. They're one of the very first animals, just after sponges. Below you have bacteria, fungi, etc. But as far as an animal with a body plan, they're one of the very first. They belong to the phylum Cnidaria that's defined by Cnidae, which are subcellular explosive stinging organelles that are shared by Anthozoa, the anemones, corals, as well as Hydrozoa, Cubozoa, not shown here, Staurozoa, as well as Scyphozoa. All of these animals have the capacity to sting. We may say that this one doesn't sting or that one does sting. In fact, they all sting. They may not sting us. So a lot of them feed on microscopic invertebrate zooplankton. But among box jellyfish, there are two main families. There are the Cryptidae and the Chirodropidae. Luckily, in Hawaii, we only have members of the Cryptidates. The most fearful paper I saw when I first did my literature search were papers about Chironix flickeri in the Indo-Pacific, in Indonesia, Thailand, and Australia, where deaths would occur in as little as 5 minutes after as little as 1 meter contact of tentacle. So that actually really gave me a moment of pause that I was fortunate not to have encountered such an animal. But again, Hawaii does not have that species. The life cycle of the Medusazoa and our Alatina alata, the Hawaiian box jelly, goes through sexual reproduction, males and females, to form an embryo, a planulae, which then settles to be a polyp and grows up and strobulates to produce a single immature jellyfish, which then matures. This is a bit of a mystery to us where this occurs, because one only sees the mature, gravid Alatina alata when they come in the 8 to 10 days after the full moon to spawn. They're beautiful animals to study offshore, so I've done a lot of nighttime photography, and this showing how beautiful they are swimming at night. Now this guy has come over the reef, and the reef fish will eat the tentacles, interestingly enough. So that animal doesn't have any tentacles that you can still see. Now there are over 40 different species of box jellyfish. This tiny animal here on the right is Civixii, Copula civixii, and it's basically as tiny as the tip of your pinky. The animal that I've been studying for 20 years almost is this Alatina alata, and it's really gorgeous offshore at night. Here's one feeding. Is that a question?
Yeah, the fish that eat the tentacles, do they make use of the stinging cells like some other animals do?
Not to our knowledge. They seem to be able to just digest them totally, so they don't repurpose them. Okay, so now what you may well know at this point is the periodicity of the influxes. So we have a paper that is under review, and basically we have others far before us, starting with Gail Grabowski and our sorry, one moment, I'll show you his photograph. Crack the code 8 to 10 days after each full moon. And basically this is the same period of time, which is just days before the new moon. Now we know that the box jellies come in Waikiki side, and it's a huge nuisance for us there. But as far as other areas on the island, we have Hanauma Bay, the west side, even up to Yokohama Bay gets from time to time. And then last summer, I had a woman bring me box jellyfish from the North Shore. I didn't believe her on the telephone, so she and her daughter got in the car and drove down, and sure enough it was. So we've sent that off to the Smithsonian to do some genetic analysis of that. But what we do know is that each of these different groups is basically its own community or cohort. It's not as though the animals from Waikiki swim all the way up to Yokohama to come in that 8 to 10 days. But what we find in common is this deep sea bathymetry. Basically, the way the ocean floor sits is almost like a basin, which creates what's called an eddy current. So there's a constitutive eddy current, this whirlwind of invertebrate zooplankton, which provides a nice stable food source. So we're starting to study more and more about the field ecology and how these animals survive and how they thrive, and what's the tipping point to make the numbers of them increase so much as we have seen occur. Now, with regard to my laboratory, we're blessed in a way that most other Honolulu folks would think as a curse by having these animals come to us every single month without fail since I've started this study in 1997. Now, as a biochemist, my work is limited by access to the creature of interest. If we were studying scorpions, we would need lots of scorpions to do the venom biochemistry. Now, you might imagine that jellyfish don't have venom glands or fangs like a snake. And the venom, in fact, is encapsulated in tiny microscopic capsules, which are very tiny. So we basically need 1,000 animals to get 2 milliliters of venom. 1,000 animals will yield us 1 billion nematocysts, from which we derive all of our work. But again, back to ground zero here, off of Waikiki in the ponds, 2 Charlie, 2 Delta, month by month, the animals come in. They're swimming against the tide. The tide's going out, they come in, and they it's almost as though this is a perfect nursery for them. It may be that the reproductive success is increased by having these walls and having low levels of reef fish, etc. But that's work that's still ongoing. So again, we now have good recognition by local television, newspapers, and internet. And the Ocean Safety has done an excellent job with communicating to the public when to stay out of the water. And sorry, I blocked on his name earlier. Landy Blair. Landy Blair is our hero. He really was the main first person to characterize these, the schedule by which these animals come in. So here, just to show you though, when I started the work, things were going up, 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 and it almost looked like we're in some kind of cataclysmic situation. But then they came down again. And now, after the benefit of 20 years of data, we can see that they follow what's called a decadal phenomenon, a deep ocean phenomenon, which actually is tied to the lunar cycle with this longer periodicity as well. So while the general trend may be going up, this waxing and waning over an 8 to 9 year period gives us some comfort that we're not at the end of the world here. So the interesting thing about these animals, besides this terrible venom, is how sophisticated and complex they are. They have 4 eye stalks, and on each eye stalk are 6 eyes. So that means they have 24 eyes altogether. And it's not up to 24 eyes. A lot of websites say they have up to 24 eyes. No, they don't. It's like humans have up to 2 eyes. No, we have 2 eyes. So they have 2 eyes such as our own, with a lens and a retina, and an iris that can constrict. They're capable of color vision, and because these 2 eyes out of the 6 on each eye stalk are oriented in a different direction, they basically are capable of almost 360-degree vision in color. They also have these ancient eyes. In terms of evolutionary time on the planet, they really recapitulate the entire history of vision. So they can detect nearly single photon amounts of light, as well as shapes and colors, and hunt prey. So it's a very sophisticated animal. And here's a nice movie offshore at night. So this is some field work I did in the Northern Mariana Islands off Saipan, and I'm tethered to a downline off of a vessel that's at drift. And we had oceanic white-tipped sharks coming in, kind of bothering us and smashing into our lead lines and our buckets, but we persevered. And this box jelly here is in the midst of feeding, so I'm swimming up to it to take some pictures and then swimming away. But you can see how long the tentacles extend. Okay, so, sorry?
How long were the tentacles?
Oh, they would extend to, I would say, about 4 or even 5 feet. It was really remarkable. Okay, so again now, my center interest in this whole effort to look at box jellyfish is really to address this global health hazard. And just to sort of bring it home to you, severe stings such as this happen. This is from Puerto Rico, the very same species that we have here in Hawaii, Alatina alata in Puerto Rico. This is a different species, but these animals account for severe stings and deaths throughout the Indo-Pacific, in the Caribbean, and now we have new reports from Brazil. It's probably, this map needs very much to be informed by better reporting. This one red dot up here, I want to point out to you, it was reported that a person in the UK suffered Irukandji syndrome. And I'll explain to you a little bit later what Irukandji syndrome is. But basically, that was not due to a box jellyfish. And we found out now that other types of jellyfish can cause this, what's called Irukandji syndrome. So I'm going to get a little bit more deeply now into the basic puzzle that motivated me to get into this field in the first place. So when I did my first literature search and I found out about these deaths that occur in as little as 5 minutes, I was doing electrophysiology and membrane proteins and biochemistry of different membrane proteins. So literature that the PET hypothesis was that these box jellies contain some remarkably potent silver bullet type ion channel blocker. That sounded good to me. So like a bird dog, I kind of went to that sort of a chase. And so I constructed all my first experiments to go look for ion channel blockers. And I did incredibly complex electrophysiological screenings trying to look for that. But unfortunately, every single experiment I did ended in what I considered catastrophic failure. It's almost unmentionable. As an electrophysiologist, one never wants to see what's called leak current. It's a non-starter. It means you got detergent in something, you have some weird contaminant. You can't do any sophisticated electrophysiology with leak current. But no matter how hard I tried, all I got was leak current. So I wrote a different kind of grant to keep going forward. But I want to tell you now, with the benefit of 19 years of work, the leak current was the answer. The leak current was the answer. My first failure, which I thought, okay, I'm done here. You know, I've got nothing to add to this body of knowledge. In the end, that turned out to be the key. So you can see here the critical clinical question that I've laid out. Now I want to perhaps bore you a little bit, but some folks may want the details here. So Irukandji syndrome is a complex sequelae, and my own clinical presentation fits this. About 1% of Hawai'i Alatina alata severe envenomation cases fit this. Extreme pain with catecholamine surge features anxiety and nausea, sweating, may present with minimal skin findings, and evidence of what's called a cytokine storm, histamine overload. That basically can lead to respiratory insufficiency, so the feeling of liquid in the lungs, nausea, backache, cardiac arrhythmias, a hypertensive phase followed by a hypotensive phase, etc. So I just want to bring your mind to this first point, catecholamine surge. Catecholamines are epinephrine and norepinephrine. And what we found is that the venom causes platelets to burst and drop their storage depot of sequestered catechols. This is a case in which you'd have a person presenting at clinic saying they're having respiratory distress and they've been stung. Well, emergency room physicians are trained to deal with bee stings, Hymenoptera stings, and lives are lost without sufficient intervention. And that intervention is epinephrine. In this case, administration of epinephrine in the Irukandji syndrome is completely counterproductive. So if the person already has a massive amount of blood surge of catechols and you inject them with more, what happens is cerebral hemorrhage and death. So I just want to completely beat that drum. Never use an EpiPen or stand by and watch one being used on a box jellyfish sting patient. There are other ways to manage respiratory insufficiency because the genesis of that is this histamine overload. So the clinical management, even if you're a bystander, it is important to have that knowledge. Okay, so back to the big picture. We've all seen this map a number of times now. So Chironex box fatalities, the larger animal, other fatalities, Irukandji fatalities, and Irukandji stings. All right, so I'm going to give you a crash course in envenomation pathophysiology. And what do I mean by that? So pathophysiology is basically the study of how things go wrong. And envenomation, you would know, is just being stung. So what goes wrong after a sting? Well, there's two major features to a sting. There's the physical trauma and then the effects of the venom. With regard to the physical trauma, the tentacle is coated with thousands to hundreds of thousands, and even very long tentacles, millions of these explosive stinging cells. Each of them are microscopic and you can't see with the naked eye. Each of them acts like a hypodermic delivery device, injecting deep into the skin up to 1 millimeter and emptying out that venom. So the physical trauma that's left behind, even if you did everything to get rid of the venom, is still going to cause you a headache. In my case, I had 4 months of raised welts around my neck that looked like poison ivy. Now, the other side of the coin is the side that is of interest to me as a biochemist again, looking at trying to crack the code of what comprised the venom in an ingredient list type of approach, and then elucidate the mechanisms of action of each of those ingredients and try to identify, is one of these the lethal component, or does it take a few of them working together to cause death? Is there any way to inhibit any of these constituents? And ultimately to develop an animal model. So this is what I thought of early on, and I'm happy to be here 19 years later and be able to now give you information on each of these. So the first thing I really got into was the cell biology and doing electron microscopy. So interestingly, this is a capsule that has discharged, and it has this lancet that shoots out like a little arrowhead, and it's very tough and it will pierce through the tissue or the carapace of the copepod. And then you have the hollow tubule itself here, hollow in the middle. And you'll notice that it has spines on the outside. Those spines keep that tubule embedded in your tissue. And the spines are comprised of minerals. So it actually has the chemical composition very similar to crab shell chitin, mineralized chitin. And that would probably give you an idea why it feels itchy after the fact. You might, if you've been on the East Coast and never had chiggers, it's a similar kind of sensation and biological response. So what do all these things look like? In the light microscope, we can just see the tentacle itself, pink, and tiny little dots. If you go up higher in magnification, you see each of those little capsules, and here they are discharged, and you see the capsule head there with a long tubule piercing through. In this case, we're using agar that has red blood cells in it. So it's a tissue proxy, it's a red blood cell agar. And now you see that when we lay the tentacle on that, it spontaneously discharges these little nidae explosively pierce through the blood agar. They dump their venom into this blood agar, and we can see a zone of hemolysis. As the red blood cells are lysed, we get this clear zone in what was a pink opaque gel. But now to back to the beach, showing you some animals fresh caught. And then I borrowed a $100,000 camera from Olympus Industrial that shoots 30,000 frames per second. It basically shoots fast enough to take a picture of a bullet coming out of a gun and having about 80 frames such that you could read the details on the bullet. But here you see that's how fast this discharge occurs. Basically, these nidae all explosively discharge, but they are held back in the plane of the tentacle. Here's one who had fallen out, but who still can discharge. Each of these higher magnification, the capsule has this spring-loaded long apparatus inside, discharges out, and the venom is injected into the prey or to this unhappy surfer at dawn. So the first thing I went about doing then was figuring out a better way to purify the venom. When I began this work, the typical methodology involved taking tentacles, freeze drying them, and then crushing them with a mortar pestle in dilute saline. That made about as much sense to me as taking a dried up rattlesnake off the road and throwing it in a blender with salt water and calling that snake venom. I mean, okay, maybe there's a couple molecules of venom in there, but it's got every other bit of the snake in it. In the case of the tentacles, of course, there's not quite as much going on, but I wanted a method to isolate individual nidae that were undischarged intact from live animals. And I wanted to be able to rupture them. And you see, these are the structural bits, the long tubule inside, and everything else is the venom. So I wanted to be able to capture that. And that isn't a nice liquid venom like one might get from a snake. It's almost, if you took a Big Mac with a cup of mayonnaise and put liquefy, that's about what this venom is. It's highly lipidic, it's very thick, it's very hard to deal with. Yes?
What is nematosis?
Nematocysts. So the nematocysts are the individual nidae capsules. Penetrant nidae are called nematocysts. So I can isolate, I've developed a method now to isolate from live animals the nidae. So we basically put it in a special solution and have it go in the cold for weeks. And we sieve that solution that comes off. The nidae are extremely stable. They can be freeze-dried and brought back 40 years later and be incredibly potent. And the trick to that is that this bit inside the nematocyst, where the venom is basically this crystalline array. It's has to be hydrated in order to become active. So it's a perfect time capsule. So we can then rupture these in mass, hard spin it to get rid of the physical bits, and now we have just the the contents, which is the venom. So this is my happiest slide here. I have to be very proud of being able to use my HPLC as a card-carrying biochemist. So this is high-performance liquid chromatography in my lab at Manoa. And basically, we can separate all the constituents that comprise a complex mixture. And your bad-natured PI as a graduate student would give you something and say, okay, solve that. So this was almost along that line, but it was nature itself giving me the solve that. So what we do then is to separate using various types of chromatography, and then take fraction by fraction and do bioassays, hot or not, hot or not. So in the biggest picture, the mouse lethal assay, this tiny fraction here was it. So you might remember a few slides back, I put the various different potential outcomes, that there could be one constituent that's lethal, or it could take a whole bunch together, or it could take the whole thing. In fact, it turned out that this is the locomotive of the complex cocktail. All these other bits are important, but they're slow acting. If you inject a mouse with this alone, you'll have the same kinetics of death as you had with the whole venom. So I was happy about that, and I ran after that in no time. So we took those different fractions and we did all these different kinds of bioassays to look at immunological responses with different cell types, and the other constituents of the venom, besides that fast-acting agent, which is called a porin. It's a protein that forms pores, and thus the leak current that I mentioned earlier. So that porin was responsible for the leak current. Lipases, metalloproteinases, and other bioactive molecules. So this is the nematocyst capsule and the tubule injected through the dermis and the epidermis, and all the way into the capillary, dumping the venom, this complex cocktail, into the dermal space, and all these things are happening. So the fastest acting agent is this pore-forming protein, the porin, which basically blows holes in everything it touches. But you still have slower acting lipases and other enzymes, proteases, which cause further damage. But the porin itself causes the mast cells to dump all their histamine, and they have all that massive histamine effects. The porin itself causes holes in the neuron cell body, which leads to the burning pain. Whenever holes are formed in neuron cell bodies, one experiences burning pain. So that's why folks will cry out, it's burning, it's burning. When these compounds reach the capillary, they cause vasodilation, diapedesis, and you have recruitment into the site and massive swelling. So you can see it's a big complex picture. It's kind of a thumbnail pathophysiology of what goes on. To show it to you in a little more elegant way, here are some electron micrographs, and you can see that the pore-forming protein in human red blood cells self-assembles and forms these rivet-like pores. Okay, these were really striking. When I first did the sequence and published the N-terminus, a colleague went and published the entire protein. Fortunately, it had that capacity, and I did some modeling right away, and I noticed that the porin, that the protein had this interesting structural motif, which looked a lot like anthrolysine O or streptolysine O, the pore-forming agents in anthrax and strep. So it's really quite interesting. Completely unlike the original hypothesis that this train is being driven by some silver bullet ion channel blocker. No, it's borrowed a trick from the bacterial tool set. So that was really quite intriguing. But unfortunately, this pore-forming protein, which we first published as describing it as a hemolysin, of which there are many in the world, and hemolysins tend to create holes in red blood cells, thus hemolysis, but not into all sorts of other cells. This pore-forming protein, however, will cause holes in any cell it touches. So when it enters the bloodstream, it can cause holes in red blood cells, causing them to drop out their potassium that they've stored, and leading to what's called hyperkalemia, which can lead to acute death, as well as the porin can touch white blood cells, causing them to drop their storage depot of cytokines and histamine, and lead to other white blood cells such as lysis outcomes. And as I mentioned earlier, it affects platelets. And in fact, the first domino to fall when we do time-lapse microscopy are the platelets. before even the red blood cells start to show. So here's a time lapse. The movie didn't work on the PC, unfortunately, but this is just before and after. And in fact, in the before, my camera wasn't fast enough. It's already affected the platelets. But here at the end of the time course, you can see the red blood cells have just become ghosts. You just see these hollow, what was once a vibrant red blood cell is now just a lipid, a ghost. So we took this information then and went about to do a model within an animal model, and this is a mouse model at JABSOM with Dr. Showitz's echocardiography lab. And basically we do simultaneous echo with EKG. So we can read the electrical signature through the paws. The animal has his paws on the copper plates there. And then read with the echocardiography, Doppler, the heart. This is contraction of the left ventricle. And what we see happening after injection of the venom is what they call pulseless electrical activity, PEA. And so the electrical activity continues after the pulse stopped. That's actually great news from a clinical standpoint, because that means that there's not irreversible cardiac damage driving this train. It is a high level of plasma potassium. So as an acute care approach, if we can push fluids and decrease the plasma potassium, we can bring that person back around. So I won't go further into that. But again, just to give you some meat on the bone here, with regard to the overall unified field theory, if you will, of this envenomation, what we see is these porins, the venom porin that caused my leak current in the beginning, can affect white blood cells, platelets, red blood cells, endothelial cells, and all these things happen. But the fastest thing that happens, and the main line that drives to death, is this potassium efflux from red blood cells, stopping your heart with pulseless electrical activity, leading to death. So I was happy from that standpoint to have been able to identify the locomotive of the train, to be able to figure out the mechanism of action. Now the next goal was to try to find ways to inhibit that protein. Yes?
Before explaining what people have, what about some of the lower forms? Like
The same, we did,
red blood cells?
yep, no, I have hemolymph, we've done all of the Doppler on crayfish, and I have sister studies that we did before we had mouse authorization. We worked with crayfish. Yes. Okay, so now we went about to try to identify potential inhibitors of this porin. So in order to do that, we need to have bioassays of the porin forming hemolysis. So we have a 96 well plate red blood cells in solution that we can treat with venom and watch it work. But this is another assay, and again, this is like Jello, an agar, and we can pour that on a microscope slide and punch a hole in it with a little hole puncher, basically, and then a little straw, and we'll take, so this is all intact red blood cells. They look opaque, healthy red blood cells in an agar. If we put a drop of venom in that, we'll see hemolysis, this zone of clear area where the red blood cells have become ghosts. And this increases with time or with dose. So we had a strong assay to go forward with. So I'll save you all the hand-wringing and years of wandering around in the desert, and we come to the nice, tidy end point where we were able to save a lethally injected mouse. Here's the time of survival in minutes at different doses of venom. And then if we inject our therapeutic agent, we basically, our mice survived beyond the time the veterinarian was willing to wait with us. So at 18 hours, we had to sack them. But it worked far better than we had ever anticipated. So we were able to identify a specific porin blocker using red blood cell assays in the lab. And then we were able to translate that into a life-saving IV therapeutic for mice. As a requirement of the funding, I had to put forward a commercialization plan to bring any positive inventions or discoveries to the market. So I wrote a business plan with folks from the business school, and we had this manufactured at UH College of Pharmacy at Hilo in a pharmaceutical compounding lab to provide to Department of Defense combat divers. So now let me bring you to sort of the sad part of the story. I thought, as a biochemist, that the hard part would be what I've just gone through, which is isolating the active compound, identifying inhibitors, compounding that, getting that into a way that could be applied and used. But no, that wasn't the hard part of the story. The hard part of the story is now. And the last 4 years, 3 years really, I guess, I've spent going to the places where this matters, where the most loss of life is occurring in the Indo-Pacific, in Koh Samui, in Thailand, and in the Philippines, and in Indonesia, Situbondo, and in Australia. When one gets to these areas, the problem is that the folks don't even make it to the hospital, they make it to the morgue. And when you look at the first aid that's being put out there, I was shocked. So in this case, apply vinegar. I agree with that. But a lot of times the folks don't have vinegar, so they go to the next step. Scrape using a credit card or razor blade. All right, so you have a little child in Koh Samui, Thailand, who's just been stung. The mother doesn't have vinegar, they have a card, so they try to scrape off these adherent tentacles and then pack ice. All right, and they're absolutely dogmatic about this. If folks don't follow this protocol, they can be criminally liable. When I saw that, I said, hold the phone. Now I have to get back to the lab and do some kind of assays to show the danger of this. I mean, it might be intuitively obvious to you folks, knowing what you've seen already in this talk, how explosive these nidae, these capsules are. Only 1% discharge upon contact into the skin. Thousands of these are left on the surface of the skin undischarged, like so many mouse traps ready to go off. If you scrape it with a credit card, or worse yet, a razor blade, you're putting site pressure on these undischarged nidae. They are going to fire. Now, the box jelly we have in Hawaii is one of 40 species. These animals in Gulf of Thailand, for the most part, are a lot worse, and the nidae are a lot bigger, and penetrant capability is much higher. So when they're doing this well-intentioned scraping to remove the tentacles, basically it seemed to me that they would be massively increasing the venom load, as they say. Then packing with ice. Now this is another huge hurdle. I never would have believed it in a million years if you told me that the hard work was not the biochemistry, but it was talking about ice. All right. So as you might remember from the pathophysiology slide, there is a reason that this pain feels like a burning pain. Basically, you're causing holes in the neural membranes, and that is interpreted by the brain as burning. The last thing a lot of people want to hear is, oh, here's a bottle of hot water, or a bath of hot water, or a hot shower, go stand there. They're thinking burning, I want ice, okay? Unfortunately, as you'll see in the next couple of slides, that is the worst possible thing. All right, so I kind of felt a little bit out of my element to get into public health policy and trying to come up with rigorous scientific experimental protocols that could drive public health policy. But if any of you right now takes your smartphone and Googles what to do with a jellyfish sting, I'm sure you're going to find, rinse with seawater, pack with ice, apply shaving cream, scrape it, all manner of these things, and she'll be right. And this is coming from Mayo Clinic. So these are, presumed authoritative sources that we rely on and our emergency caregivers rely on. Unfortunately, for the most part in the US, stings are just a nuisance. But when people in Thailand and Indonesia rely on the US for information and they find these things, then we're in trouble and children end up in the morgue. So that definitely pushes my buttons. Worse than that, there's also muddying of the water even with regard to vinegar. So there are folks now who say don't use vinegar. In fact, I think Divers Alert Network still has Physalia, man of war, is a no-go for vinegar, that there are certain species that you must not use vinegar. We have a paper that's in press now related to Physalia, and I'll spill the beans on that. Vinegar works well, perfectly. It is far better than anything else. So the papers that had led to this misinterpretation about vinegar, I'll talk about those problems in a moment. But this is now a whole different side to my career, if you will, but it's a very important one. So one of my colleagues recently published a paper in a small journal, Hyperbaric Medicine in New Zealand, that led him to put out a press release on the front page of the Sydney Morning Herald that vinegar can kill. And unfortunately, folks who didn't read his paper critically took that end point that vinegar could kill and ran with it. And unfortunately, in a few slides, you'll see how the lack of vinegar, in fact, can kill. But how do things go that wrong? Well, basically, the folks presented a small study with a placenta membrane and a tentacle that's being stimulated by a 9-volt battery. And they rinsed with various things and found vinegar yielded more activity than seawater. Well, I would argue that that's because vinegar is a better solvent for the venom. Not that it caused things to go worse, it actually removed more of the poison. But in any event, the experiments later that I've done speak for themselves, as do 40 years of literature and case reports of use of vinegar on the beach. If what that fellow had said was true, we would have seen people dying along the way after being exposed to vinegar, and we haven't. Okay, so now just to sort of step back and go to the 30,000 foot level again. From the first aid point of view, which I'm sure all of you in this room are incredibly interested in, we would think, first of all, we want to prevent further venom injection. We don't want things to get worse, okay? And we want to inhibit or decrease venom activity that's already injected. These are two very different things, all right? So will the credit card help you prevent further injection? No, site pressure will not. Will vinegar? We'll discuss that. Will ice inhibit or decrease venom activity? Will shaving cream? Will peeing on it, etc.? So one needs a rigorous scientific tool, an assay, in order to address that. So I don't want to bore you too much, but these are all published, and if you're interested, you can find these in my publications. But basically, this is the authentic sting. Here's your Chironex stinging a child, and death can ensue. What we want to know, without using children or using people and doing sting tests, is can we create an assay which pretty well recapitulates what goes on here? Now, in a sting trial, one can do that to a certain extent, but of course there's ethical issues, and in dangerous stingers, one might not want to do that. So what has happened is that there's been about 20 years of literature that has just been based upon tentacle solution assays. And what does that mean? Just cutting off a piece of tentacle, dropping it into a petri dish with water or alcohol or vinegar, and reporting in the literature what goes on. So this is the place where the wheels have fallen off the bus, because people have taken Physalia, the man of war, and added vinegar to that, and found that they saw discharge, stinging, in the microscope. Unfortunately, it was diluted vinegar, or it was vinegar made with acetic acid and distilled water in the laboratory. It wasn't true vinegar. And there was also pressure involved, and pressure will cause discharge. So there's all sorts of caveats to the way these things were done, and they are not reproducible. So this becomes a major dilemma for folks like the Divers Alert Network. What do we tell our divers? Here's a publication that now tells us vinegar is not good for Physalia, and we're not scientists. So the job is back on to the scientists such as myself back in the lab. Okay, get in there and figure out a way to bring some clarity to this story. So what we've done then, and we've recently published on this, is develop a brand new assay, this blood auger assay, which I've already shown you previously, and it's remarkable. I discovered this on accident. I had some blood plates, and I just thought, I wonder if the tentacle will sting this if I crush it, and I had a battery ready to go and all these things. I didn't have to do anything. I just laid the tentacle on the blood auger, and the Cnidae have sensitive, they can basically taste chemosensor and mechanosensors, and the chemosensors were activated just by proximity and being laid onto the blood auger, and they discharge. So we've counted the number of Cnidae that discharge per unit length, and it's indecipherable from human skin. So this is a breakthrough discovery. Now, that said, you can imagine if you have a piece of Jell-O with blood in it and you lay a tentacle on it, you can't very well spray it with vinegar because the vinegar will get into the Jell-O. So we created a skin. We used a surgical methodology that is for burn patients, basically taking small intestine from piglets, and we treat that with ethanol and hydrogen peroxide to sanitize that, and then rub that with sterile anhydrous lanolin to create a barrier function. So we have a proxy for skin. Now we can lay that over the blood auger, and then the question was, well, will it still sting through that? Well, it did. So now we have a wonderful assay that we can go through and rigorously test all these different approaches that have been proposed. The animal assay, which I've showed you previously, and then the next level is to use animal modeling, laying a live tentacle onto the animal. But for now, I'm just going to talk to you about the blood auger assay. So the goal was to come up with evidence-based first aid for preclinical and clinical treatment. And the barriers, as we mentioned before, were lack of reproducible models. The answers that we came up with is a tentacle solution assay with specific a protocol that can be reproduced in other laboratories, as well as this blood augurose and skin blood augurose assay. So I'll go faster now so you don't fall asleep. But this is all recently published in this paper. And again, I mentioned to you that it stings the same amount per unit length as will on skin, and what it looks like, the skin over the blood auger. Okay, so now this is the technology that I had previously developed into the cream. And here you see the imprints of 2 Cnidae that have discharged. And you see all those healthy red blood cells everywhere? It's not lysing the red blood cells. So the same technology that saved the mouse life saves these red blood cells in this blood auger assay. Whereas in this case, the blood is completely lysed. You only see a couple red blood cells left. So now we could go back and say, what will happen if you scrape or rinse with seawater or vinegar, etc.? And we can count the amount of basically the area of hemolysis. Now here you see what happens when you scrape off a tentacle. Basically the tentacle rolls, as do the Cnidae, and with the site pressure, it causes them to discharge. So this poor child who's getting his leg scraped is getting a massive increased dose of venom. Now you might think that rinsing with seawater would be innocuous. It comes from the sea after all. But in fact, what happens is that all this area gets lysed, and here it's kind of hard to see it diffuse because the Cnidae get spread everywhere. They basically are happy to be spread around in the seawater, and then they fire off more, versus being pulled off or treated with vinegar. So what does this look like with proper statistical powered studies? Basically, here is seawater rinse with scraping to remove tentacles. So the higher this is, the more hemolysis, the more damage is going to happen to the tissue. That's the worst thing we could do. Now here you are, vinegar rinse and scraping. The vinegar actually bought you time, and the vinegar is an irreversible inhibitor of the Cnidae. It causes the collagen to swell, and it prevents discharge. So undischarged Cnidae, but vinegar won't get into the skin and won't heal or reverse venom effects that are already in the epidermis and dermis. And then here we have ice versus hot. So when you do heat, here's the level of hemolysis, almost zilch. Whereas with ice and ice with scraping, you can see what's going on. So there was a sudden uptick of deaths in Thailand after adoption of those protocols, and now we can really sort of drill into that. But what does this mean for the fellow at Hanauma Bay who gets stung and comes to the lifeguard stand and says he doesn't want hot water, he wants ice? Do we care? Does it matter if he undergoes this or that? Well, I would say that the good news, it's a good news, bad news situation. I would say that the good news is that in Hawaii, because we rarely have sufficient envenomation to cause severe sequelae, that letting the patient drive the train may not lead to his death. On the other hand, there is irrefutable evidence that he's not going to fare as well. So it would behoove us and those in the audience who may be more skilled at public communication and public health policy to somehow be able to communicate to the fellow who's coming out of the water the seriousness of his decision. This isn't like a sprained ankle on the side of the basketball court where it doesn't really so much matter if we put an ice pack or a warm pack, although some coaches might disagree with that. So here's just some plates to show you how that looks. So here's cold, ice treated versus hot. So it's just a remarkable difference. And I'm going to go a little faster because I think I'm running out of time. Now, I was able to finally accomplish a life dream last December. I got to Australia, Cape York, up near Papua New Guinea, the very tip, where the Chironex flickeri, the huge basketball-sized box jellies, are in abundance, as well as 15-foot saltwater crocodiles. And I got to do all of these experiments with Chironex, live Chironex tentacles. And the question was, will the same hold true? Or, as the other fellow had published, will vinegar cause things to get worse? Okay, so this is really critical to the talk. Here's Chironex from Weipa, Mapunu, Cape York, Australia, versus our local Alatina. Pull, and this is the level of hemolysis, and we want things to be on the bottom of this control panel. That's the level in the control. So we'd like things to be less, right? So here's pulled off. Now, scraped off is far worse again. Rinsed in seawater, worse. Rinsed with vinegar, better. And the technology that I developed, which we saw in the red blood cell, completely prohibits venom activity. So vinegar itself isn't going to get into the skin, but this technology will. Here we have in Alatina, scraped off, much worse. Rinsed with seawater here. And here is the vinegar and the sting no more, and far worse with ethanol. Okay, so I'll run as quick as I can. So back to the nail that I'm going to bludgeon to death, the heat versus ice. Okay, so it's not going to be scalding. It's not too hot. It's within the legal limits for plumbers. It's not as hot as will hurt your child. And it has been published again and again. Here in Snakebite book with regard to jellyfish stings, use heat. American Heart Association, other folks have noted that heat inactivates the venom, Hong Kong, and others' data. So with regard to ice packs, in randomized controlled trials, none of them recommend ice packs. With regard to hot water immersion, all of these. So food for thought, I think it's a big problem for Hanauma Bay. And if you want to look into more of my papers, it gets a lot more complicated, but I won't go into all of that. And then here's some work up in Australia, and the final recommendations: rinse with vinegar and hot water. If you had this technology, use that. Avoidance is best. The spray and the cream, or other options, the vinegar and hot water. Don't use EpiPens and don't scrape. I've worked with folks from Combat Divers, Department of Defense, and Diana Nyad. I was her diver and gave her the technology to get. So work in Ireland. I mentioned earlier that we had an irukandji case in Ireland. It was due to lion's mane. So we've done the same work with lion's mane, and again, the heat inactivates the venom. So thanks so much for your attention. It's a real pleasure to be here. I'm happy to take any questions.
Dr. Yanagihara can address any of the questions that you have by the water cooler there. If you could lend a hand to put back the chairs and put back our rails for operations tomorrow, that would be wonderful. Thank you. Enjoy your evening. That was great. Let me just turn this off.